Ma'am, I created the YouTube link, ma'am. I kept in chat box, ma'am.
Thank you, Sampurna.
Okay,
We'll
ma'am.
share in our class
Okay,
groups.
ma'am. Ma'am, I'm making you as a host, ma'am.
Okay.
Okay, ma'am. Ma'am, down, are you able to see N, ma'am? N button now? Ma'am?
Jyoti ma'am. Ma'am, చెప్పండి.
కింద N button కనిపిస్తుంది ప్రసన్న. Jeevanjyoti ma'am కి కనిపిస్తుంది. Ma'am host కాబట్టి after completing meeting you can click that N button.
Okay, okay, Sampurna.
Okay, ma'am.
I'm leaving, ma'am. I'm leaving, ma'am.
Okay.
I'm making recording on cloud, ma'am.
Okay.
Ma'am, now you are having permissions, ma'am. You have to record it, ma'am.
Okay.
You are the host, ma'am.
Okay, once it starts, I have to press the button, right?
Record button, you click it, ma'am. Just.
Okay. Okay.
Thank you, ma'am. Bye, ma'am.
Okay, right. Right. Ma'am, shall we start, ma'am? Haripadma Shri, ma'am. Madam?
Hello, Jyoti.
Ma'am, shall we start, ma'am?
Yeah, just give me 1 minute. You can start.
Okay, ma'am. Okay.
Just want to fix up something. Yeah, please carry on, Jyoti. Thank you.
Okay, ma'am. Thank you. Good morning, one and all. I extend my hearty welcome to today's guest speaker, Dr. A. Haripadmashri, ma'am, Assistant Professor, Department of Chemistry, Usmania University. I would also like to welcome Professor Sudarshan Reddy, sir, Secretary and Correspondent of the college, Professor Mucham Reddy, sir, Secretary, HMVS, Dr. Achita Devi, ma'am, Principal, fellow colleagues, and my dear students, to the guest lecture on thermodynamics organized by Department of Chemistry. It gives me immense pleasure in introducing today's guest speaker, Dr. A. Haripadmashri. Ma'am obtained MSc Physical Chemistry from Department of Chemistry, Usmania University, Hyderabad, and got GATE qualification and then joined for PhD at CSIR IICT Hyderabad. Her topic of PhD was hydrodechlorination of dichloro-difluoromethane over calcined magnesium aluminium hydrotalcite supported palladium-based catalyst. After completing her PhD, she joined as research associate at IICT and then as pool officer under Scientist Pool Scheme CSIR at Usmania University and later as DST Women Scientist at IICT. She was recruited to OU services as an assistant professor in 2007 and worked at Usmania University College for Women till 2017. And now ma'am is currently working at Department of Chemistry, University College of Science, Usmania University main campus. Madam has 14 years of teaching experience, both in UG as well as PG, and taught almost all the fundamental topics of physical chemistry. Her research experience is about 20 years in the area of catalysis, nanomaterials, and sustainable energy. She is a registered guide of Usmania University and is currently guiding 7 students. 2 of her students completed their PhD under her supervision. She has published 45 papers in international reputed peer-reviewed journals, of which 1 paper is with a highest impact factor of 16.683, 16 papers with more than 4 impact factor, 31 papers with more than 3 impact factor. And the papers have H index of 19, I-10 index of 28 with 1765 citations. She is a co-inventor of 3 Indian and 3 US patents. She has received several oral and poster presentation awards in national and international symposia. She completed 2 major research projects, and one of them was collaboration with Ireland under India-Irish bilateral program funded by DST New Delhi. She is currently working on projects under OU DST, PERS 2, and OU UGC FAR programs. She is a life member of Catalysis Society of India, Indian Science Congress Association, Indian Association of Chemistry Teachers, Usmania University Chemistry Alumni Association, International Society of Teachers and Researchers in Chemistry, Journal of Teaching and Research in Chemistry, Indian Council of Chemists, and Associate Fellow of Telangana Academy of Sciences. She presented papers in many international and national seminars and delivered lectures as a resource person in workshops and webinars, and also gave extension lectures at various UG and PG colleges. She received articles for She reviewed articles for Elsevier journals like Catalysis Today, Modern Chemistry of Science Publishing Group USA, Bentham Publications, International Journal of Photochemistry and Photobiology, the Science Publishing Group USA, Journal of Heterocyclic Chemistry, and many more. She also reviewed MS dissertation. Administrative positions at University College for Women as in-charge head Department of Chemistry, controller of examinations, placement cell member, coordinator of research and innovative program cell, under which she conducted many seminars, faculty development programs, and skill development programs for students. She served as a member of Departmental Committee of Chemistry, Usmania University, and currently serving as a member BOS PG Chemistry, Usmania University, member BOS of Department of Pharmacy, Telangana University, and VBIT. Presently, ma'am is serving as the student placement in charge, and also the student coordinator for Department of Chemistry, University College of Science, Usmania University. Now, with this brief introduction, now I welcome once again Dr. Hari Padmashri ma'am, and I request madam to please deliver the lecture on thermodynamics. Thank you, ma'am.
Yeah, thank you very much, Jyoti. I didn't want to interrupt you, but yeah, thank you very much for your kind introduction. And I'm very grateful to RBVR College. I really appreciate the way you've been conducting several programs, webinars. I mean, all the departments, and especially the chemistry fraternity of this department. I've been observing. I mean, I'm associated with many of your members, so I know. So you're doing a great job. I really appreciate the way you've been conducting several programs benefiting the faculty as well as the students. And thank you for the invitation. Yeah, can I share my screen now?
Yes, ma'am. I stopped my share.
Thank you. Yeah, is it visible?
Yes, ma'am, it is visible, ma'am.
Okay, thank you. So, as being told to you, firstly, I would like to make it very clear that my lecture is mainly intended for mostly for the UG students. So, I've been told that both UG as well as the PG students are attending this, but I think it is more sort of a revision to the PG students, because if I have to satisfy both, it is not quite possible, because I go with the higher concepts of thermodynamics. It would not serve the purpose for the UG students. So I have taken, but for the benefit of the PG, I'm also taking a few concepts of thermodynamics that would interest the PG students as well. Yeah, thank you very much. Firstly, Dr. Jyoti, for inviting me to deliver this lecture. Right, so let us get into the lecture. Yeah, I'm not here to give any moral lessons, but it's always good to start with a good saying or a quote. So I believe this should be the very motto, and I think this explains the role of students. I mean, the the time now you are in such valuable, that how you have to utilize it to get on with your career. So how precious it is, you should understand, because this is the stepping stone. Now you're going to make your careers based on these years of your studies, right? So yeah, start with the quote by Swami Vivekananda. So I feel that if you intend to, if you are eager to learn, so nothing is impossible for you to crash. So with this positive saying by the great man, we will start. Thermodynamics. So it is formed from two words, thermo and dynamic. So firstly used by Thomson, who is also became a Lord Kelvin, was called Lord Kelvin later. It has got the Greek origin saying, so these are the Greek letters saying thermi, that is heat, dynamics, that is anything which is in power, which is in motion. Okay, so this is the image of the scientist, the great man, Thomson, Lord Kelvin. So who used this term thermodynamics? What is this thermodynamics? This deals with heat, work, and those properties of matter that relate to heat and work. And overall, you can say thermodynamics is one which deals with energy, any form of energy. And this is the basic science, or the basic one which is required for any physical and chemical process. Knowledge of thermodynamics is required for any physical or chemical process to happen. So this is a fundamental concept, fundamental science that a physicist or a chemist or an engineering student or an engineer or a metal science person, everybody should know. So this is one of the core and fundamental concept or the science that one should know. So what is it interest to? We are we are from chemistry background, right? So what is it interest to the chemist? So the fundamental questions comes to a chemist. When chemist, what does a chemist do? He performs reactions, right? Carries out reactions. So what is the basic thing a chemist would look into? Firstly, he would try to understand. He wants to perform a reaction. He first would like to understand why does a reaction happen. The basic knowledge before he carries out a reaction, what is the basic knowledge he should have? Why does a reaction occur? What is the driving force? How far it can occur? To what extent? What rate it is taking place? Whether the reaction takes place or not when performing a reaction, right? So all these answers, you get it from thermodynamics. So thermodynamics is the basic science that gives you information regarding whether a reaction happens or not, what is the driving force behind it, etc. But of course, it doesn't talk about what rate at which the reaction takes place. There is another branch that deals with this, that is the chemical kinetics, which deals with the rate of the reaction, right? So coming to the significance of thermodynamics, why at all we have to know about thermodynamics? When you look into the world anywhere today, anything around you today, everywhere you find thermodynamics, because I said any physical or a chemical process involves the principles of thermodynamics. So if you do not have the proper knowledge of thermodynamics, for example, you have an exothermic reaction going on. So you know that what is an exothermic reaction, which gives out a lot of heat. Now you don't know before performing the reaction that it's an exothermic reaction. What will happen? So it can go out of the control and accidents can happen, explosions can happen. Now, so the knowledge of the thermodynamics, the principles behind any process is a must today. This simply, I just wanted to show you some pictures where, if you don't have the knowledge of the thermodynamic process, thermodynamics of any reaction, what can happen? For example, see, I'm not going to read out all these things. I'll just show you the pictures and tell you. So these are some of the big accidents that have taken place in, big great cities like New York. That is collapse of, we know the collapse of the New York Towers, World Trade Center, the burn down of the Dubai, this downtown hotel, that's a huge building that is there before Burj Khalifa. This was one of the tallest buildings there. And Grenfell Tower at London. Okay, so why this kind of fire? Of course, World Trade Center, it is because of the attack of the terrorists. But can you see there are two different kinds of fumes coming out there? There is a white and the black fume. So initial fire started with something, but there is lot of what is known as aluminium cladding that is there. So aluminium cladding is between the aluminium panels. You have the LDPA, the polymer, sandwiched in between. So what is happening here? The aluminium, you know that aluminium is inert when it is in the metallic state, but when it is melting down, when it is when it melt down with the initial heat, what happens is it is triggering the other kind of exothermic reactions. That you can see that this is the other kind of fumes that are coming out, this white fumes, forming the aluminium, which is there, it is forming the dust with alumina powder, that's aluminium oxide dust, aerosol powder, it is formed. So it is this aluminium fire, what is it? When it is combined with water. So if you have no knowledge what type of fire extinguisher, that means what, if you have no knowledge of the thermodynamics, that means exothermic, endothermic, what is the heat involved, etc. of the reaction, then you're using an improper extinguisher or there, if you use water there, what is happening? That water further is enhancing the fire. It is acting as what is known as the aluminium fire. Actually, this aluminium fire is nothing but a kind of a rocket fuel, So if you have no proper knowledge of the reaction, thermodynamics happening there, then what happens? The unnecessary further, the reactions trigger up. What is supposed to be used there actually was the CO2 foam powder extinguisher was supposed to use, but if you use that water extinguisher, so water is not the answer for everything, right? So yeah, you could see that there are two different smokes over there, the black smoke, the black residue, and the white, which is corresponding to the aluminium oxide, that is aerosol fumes that are. So several hazardous reaction takes place, the exothermic reactions. For example, water is poured into acid. You can see heat is, so you should know how to mix when you're diluting the acid. How do you dilute it? So you don't just pour off, water just like that into the acid. Very carefully, into the water, you should start adding the acid. So you should know how to, because when do you know that? When you know that it's an exothermic reaction, what is the thermodynamics behind the reaction, like that. Okay. And for example, sodium metal, you know that sodium metal cannot be kept out like that in the atmosphere or in water. It's highly vigorous reaction, explosive reaction can take place. That's why we store sodium in kerosene, right? But what happens if you have no knowledge of this? What happens when, whether it's an exothermic or an endothermic reaction? Even certain endothermic reactions can be dangerous. Suddenly, they take up a lot of heat, and then they can be disastrous reactions taking place. And thermodynamics, of course, is the core part to understand any living process also, and all the biological reactions, they are also governed by the laws of thermodynamics. So in a way, we can say thermodynamics is one branch which is law-abiding branch. So all laws. So you can say thermodynamics revolves around three main laws. So this whole lecture, actually, I'm going to talk about those three laws. And through those three laws, what concepts you get and how you apply those concepts in understanding the reactions. Okay. Yeah, these are some of the examples where biological energy transformations, any process, I told you, physical, chemical process, involves energy, right? So thermodynamic principles are involved everywhere. This is one example of a highly exothermic reaction. So you should have a knowledge. This is oxidation of ethylene, unless you have the knowledge of these thermodynamics of a reaction, so it becomes difficult to understand and control the reactions. That way you can say that thermodynamics is significant in every process, physical or chemical process, right? So before we actually go into thermodynamics, we need to understand certain terminology associated with thermodynamics. What do we use generally? A system. The matter under consideration which you are studying actually is called a system. Everything around it's called the surroundings. Okay, so everything around that system. System is the part which is under study. Okay, a system can be as used as a big stadium to a small conical flask. Okay, right? What is the region or what is the system you are studying? Is your what is the matter you are studying? It becomes the system, and rest whole universe becomes surroundings. But we don't consider whole universe. That is the nearest surroundings that can influence much extent is called the surroundings. And the the line that is dividing these two, the surface which divides the system and the surroundings, it's called the boundary. And of course, you have mute yourself. Okay, so system, you have basically, you divide them into three. There are three types of systems. One is the open system, where exchange of matter as well as the heat takes place in an open system. Where only heat can be exchanged and not the matter, that's called a closed system. A system where no exchange of heat or matter takes place is known as an isolated system, right? And of course, boundaries also, depending upon the nature of the wall that is separating. It can be a rigid wall based on its shape. There is no exchange. It's impermeable wall. which prevents the passage of matter, permits energy. Rigid wall doesn't permit anything. Permeable, it permits the passage of matter as well as it's more of porous in nature. Matter and energy, it's a permeable boundary. Adiabatic boundary, it's a wall that prevents passage of mass or energy. Okay, and diathermic, it's a wall that allows passage of energy but prevents the passage of matter. So it's more sort of a impermeable but not adiabatic in nature, right? Then you also have processes, various types of processes. That is, you can have adiabatic, isochoric, isobaric, isothermal based on the conditions, the variables, right? So you have a process. See the thermodynamic system. Yeah, another thing I forgot to define. How do you define a system? System is defined in terms of its thermodynamic variables. What are the variables? What do you mean by variable? Variable is which changes all the time, right? So what are the variables here? You have volume, pressure, temperature, density, composition, all these things are the variables, right? So one system differs from another system with this variable. For example, water at 1 atmospheric pressure, 10 degrees centigrade is, you can say that is the state of the system, and other state of the matter, sorry, I was talking about the state, not the system. The state of the matter is defined in terms of its thermodynamic variables. That is, water at 0 degree centigrade is one state, same 1 atmospheric pressure. Only what has changed? Temperature. The same water at 10 degrees centigrade, 1 atmospheric pressure is another state of matter. So there is change in one or more variable that gives you different what you call states of the system. Okay, so that is the thermodynamic state. So here, based on the kind of variable that is acting, you have different types of processes. For example, you have a process where volume is kept constant and other things varying. It's called an isochoric process. Okay, that is dV, change, small changing volume is 0. Then dP, that is when the pressure is constant, no change in the pressure, then it's known as an isobaric process. Temperature is kept constant, it's called an isothermal process. The heat is kept constant. Okay, there is no transfer of heat between the system and the surrounding. Okay, it's not going in and out of the system, then it's an adiabatic process. So constant heat process is an adiabatic process. So you can see here in the graph, pressure, volume, different isochores, adiabat, isotherm, isobar, they have been shown here. You can also have what are known as reversible and irreversible processes. What do you mean by reversible process? If a system is going from state A to B, and if it can return back from B to A as such, okay, it's called a reversible process. But if it cannot, then it's a irreversible process. And most processes are irreversible, and all your natural processes are irreversible. For example, a tree is growing from seed, grown from seed, but it cannot go back to the seed state from tree to, so it's irreversible. A baby is growing into a man cannot go back to become a baby. So all natural processes are irreversible in nature. Okay, and how is this reversibility? Reversibility is more like an ideal thing, but reversibility can be attained in small infinitesimal changes. That means, for example, a gas is expanding. Okay, so from a pressure of what we say 10 to 1, you're releasing the pressure. The gas is expanding 10 to 1 atmosphere. So what happens when it is expanding, when any process is happening, you have so many molecules involved in that, in layers and layers. So right, so initially the first which is closest, when the, how do you expand the gas, already there would have been some pressure. If you release that pressure like a piston, if you release it, what happens? Immediate contact molecules with the piston will slowly first rise up. So what happens? Slowly this gas starts expanding and it attains the pressure of 1 atmosphere, right? From 10 to 1 atmosphere. But then suddenly again, you want from that 1 to 10, suddenly cannot go back to a pressurized state like that, right? Unless some externally it is a sudden, in the same path, it cannot go again. So how do you attain that reversibility? In small lots. That means slowly what you can do, you can pressurize it from 1 to say 1.5 to 2.5, like that, in much smaller changes. Those are called infinitesimal small changes. The reversibility can be attained, but at a stretch, this reversibility cannot be attained. So it's more sort of an ideality. So if it is traveling from A to B and B to A, the states, the same path it cannot take again exactly when it is reversing. So reversibility to speak, it is exactly not attained. So those are the reversible and irreversible process. And spontaneous, non-spontaneous. What do you mean spontaneous? The name goes on its own. The process is happening. For example, you put an ice, you take it out from the refrigerator, keep it on a table. Simply it melts on its own, right? The phase change is taking place on its own. But you cannot freeze the water in a vessel to ice without an external force applied on it. Itself cannot go into the solidification state. It does not freeze on its own water. So that's a non-spontaneous process. Spontaneous is where the process takes place on its own, right? Non-spontaneous is a process which cannot happen on its own without the external agency applied on it, okay? Acting upon it. Then about thermodynamic equilibrium. So we know about the equilibrium reactions when you have a forward and a backward process taking place. So when the rate of the forward and the backward process are equivalent, you say that the system is under equilibrium state. So, but when you're talking about thermodynamic equilibrium, the system is said to be in thermodynamic equilibrium when it is satisfying these three equilibrium. What is that? There should be a mechanical equilibrium, a thermal equilibrium, chemical equilibrium. Mechanical equilibrium is through work and heat conversion, right? So, or energy transfer. So that should be on both sides when it is happening at the same rate. That's mechanical equilibrium. Thermal equilibrium, that is heat transfer from one forward to backward are done at the same rate. Then you say that that means hot body is losing to cold body again, taking that energy, losing its, it's getting heated up like that, process from A to B and B to A, they are happening at the same rate. Chemical equilibrium, of course, rate of the reaction, reactants are converted into products, then the products again converted back into the reactants. That is the forward and the back process happening at the same rate. In each case, the rate of forward and backward is the same, but one is involving the mechanical, it's only the heat, energy, another form heat, the other when it is the chemical transformation. Chemical equilibrium means it should involve some kind of chemical reaction or chemical transformation, right? So then only when all the three are attained, you can say that the system is said to be in a thermodynamic equilibrium. Then state, I already told you, it's a condition of the system, that means defined in terms of its variables. That is a function of pressure, volume, temperature, etc. The state of a system is defined in terms of its thermodynamic variables. So then you have thermodynamic properties, various properties which depend upon these variables. Okay, these variables or the properties, if they depend upon the amount, okay, that is how much amount is taken. So if they depend on, for example, you take the heat content of 1 gram is not same as that of the 10 grams, right? So then that heat content, it becomes an extensive property. But if you take, for example, temperature, pressure, density, etc. These properties, whether you take 1 kg water or 10 kg water, you are actually measuring its intrinsic property over there. So it's not going to change. Temperature is the same whether you take 1 liter water or 10 liter water. Similarly, density. When you say density of water is 25 degrees centigrade, right? Whether you take, 10 kgs of, water or 1 kg of water, the density is the same. Similarly, like, heat content, of course, is extrinsic, but if you take heat capacity then becomes, because heat capacities are defined for per gram or molar heat capacity for per mole. So they become the intrinsic properties or intensive properties. So those properties which depend upon the mass content, they are called the extensive properties. These are some of the examples like energy, entropy, etc. and all that. But which do not depend upon the quantity, they're because of the intrinsic nature of the substance. Okay, so those are the intrinsic or intensive properties. Then the functions, the thermodynamic functions, we come across various thermodynamic functions. What are those thermodynamic functions? Those functions which depend on the thermodynamic variables like internal energy, enthalpy, entropy. These things are the thermodynamic functions. They can be of two types. They are either state functions or path functions. Now, when you're saying functions, because function of the thermodynamic variables, that means they depend on the state of the system. So state, I said, is defined in terms of the variables. So that is at one temperature to another temperature or one volume to another volume, the system is undergoing change, right? So the function, if it is varying only with respect to what is the initial state and the final state. So whatever it may be the path taken, whatever the route it is taking, if it doesn't depend only on, if it only depends on the initial and the final state, then you call that particular function as a state function, like your internal energy, enthalpy, entropy, all these are all the what is known as the state functions. Whereas you have certain functions which depend upon the thermodynamic functions, which depend upon not only the initial and final state. Obviously, any function, it depends on the, any quantity, it depends on the initial and final state. Not only that, if it is also depending upon the path taken, they're very specific to path taken. So it is not the same when you take path 1 to the path 2, then such quantities are called the path functions. For example, you have heat and work. These are the path functions. Mathematically, if you are speaking, okay, you can say that the function is a state function when it's an exact differential. Okay, we call it exact differential, and we represent, see, you should understand this difference. I think all of you, I don't know if you are told about this. If you're representing small d, that means you're talking about small change, infinitesimally small change. That means, say, when I'm saying dt, that means temperature is changing from say 10 degrees to 10.1 degrees or even much less. That's called a small change. But when you want to know the total change, that is, a system is going from 10 degrees to 20 degrees, in small changes you can measure. It's 10.1, 10 to 10.1, 10.1 to 10.2, 10.2 to 10.3. Like that, you go on with be doing small changes. That is dt when I'm talking about temperature. Similarly, you're talking about the infinitesimally small changes with respect to the internal energy of the system. That is, the internal energy is represented either by U or certain textbooks, it refers to it as E. So anything you can use. So it's a state function. That means it depends on initial and final state. So if you're representing with small d, that is differential, it is when you're talking what is the physical significance of differentiation? You're talking about the infinitesimal small changes. When you're talking about infinitesimally small changes, you represent it with small d. So all state functions can be represented as small du, dt, ds, dg, dh, like that. But work and heat cannot be represented as d, q or dw. You are writing dou. This is the symbol dou, which indicates that they are inexact differentials or path functions. So that is the difference. Exact differentials you can represent it by small d, but you cannot represent the inexact differentials. You have to represent it as partial differential form, that is dou q or dou d or dou q or dou w. When you're talking about dou means it's partial differentiation, partially only it's changing, right? Okay. Then if you want the total change, final change, total change, see the system is going from a temperature, I said 10 to 20 degrees in the total change you want, then you use integration. Integration is used to integrate, as the name indicates, adding up. So if you add all the small changes, that is 10 to 10.1, 10.1 to 10.2, 10.2 to 10.3, all those small changes, small differentials, if you add up, then you will be getting the differential. That is, this is capital delta. This symbol triangle, what you see, this is the this is delta, capital. So this is indicating delta U, means that is total change. Adding up all the small changes, infinitesimally small changes, you get. Okay, so I hope this is for the benefit of the biology background students. I'm telling you, physical significance you should understand. Mathematically, yes, you're talking about differentiation and integration. When you're talking about small changes, it is differentiation. And when you want total change, you integrate it between the limits. What are the limits? I mean, what change you want to study it from which temperature to which temperature, which volume to which volume. So like that. So initial to final. So you have to mention those limits. Yes, as I said, thermodynamics revolves around the laws. So start with the first, actually this is not a law. That's why they have named it Zeroth Law later. So this is not exactly considered as a law, but that's why it's called the Zeroth Law. So what does this Zeroth Law state? That if two systems are in thermal equilibrium with a third system, then they are also in thermal equilibrium with one another. That means, say A is in thermal equilibrium with B and A is in thermal equilibrium with C, then B and C are also in thermal equilibrium with one another. So this is, for example, you say you dip a thermometer in A, okay, it is reading the temperature of A. It is, say the temperature is say 10 degrees centigrade. You're dipping this thermometer in B, it's showing 10 degrees. That means what? The mercury in thermometer is in equilibrium with this object B and object A, showing 10. So it indicates that this object A and object B are also in thermal equilibrium with one another. Same way here, this beakers, what you see, they are internally connected. So A and B are in equilibrium and B and C are in equilibrium, same temperature. Then obviously A and C also will have the same temperature. They are also in thermal equilibrium with one another. Then first law of thermodynamics. First law of thermodynamics, of course, it is nothing but your law of conservation of energy. That it says the first statement is the energy can neither be created nor destroyed, or the total energy of the universe is retained constant, or the other important form which talks about the transformation of energy into heat, or heat into work. That kind of a interrelation was established based on this first law of thermodynamics, that Q is equal to delta E plus, actually it's written as A. A is nothing but you can write it as W also, right? So it is the work done. The work done is given by, if you're talking about the pressure volume work, P delta V. So there is a change in volume, which is leading to the change in the work done. So, yes. So the heat is related to internal energy and work. So work can be adding up to the internal energy or done at the expense of internal energy. Okay, so what do you mean by that? The work can, you have system and surroundings. The work can be done on the system or by the system. So if the system is doing the work, so it has to use up its internal energy. Okay, then it has to do the work. But if it is done on the system, what is happening? From the surroundings, it is acquiring the energy. So based on that, the heat or heat is taken in. So the sign of the heat upon whether the work is done by the system or on the system. So by convention, done by the system is work done by the system is taken as negative. On the system, it is positive. Excuse me. Okay, right. So first law, you can show it this way. So from one state to another, when a system is moving. So what is happening there? There's a transfer of heat or work done. So it's by the system or on the system, depending, I just told you, right? Depending upon the work done by the system or on the system, the heat is transferred or heat is acquired. Okay. So it gives a relationship between the heat and work. The first law of thermodynamics, it has introduced certain terms, that is internal energy, heat, work, and a mechanical equivalence between heat and work. Okay, so when work is converted into heat, this ratio, it was found to be, that is work to heat produced, it is found to be always constant, known as the Joule's constant. So there comes your Joule's constant, J. So this is Joule's mechanical equivalence of heat. Okay. And what is internal energy? We introduced the term internal energy, U or E. It is nothing but the sum of all the kinetic and the potential energies of the system. So it is the total, what all the energies that are there associated with the system, all the rotational, vibrational, translational. So that contributes to this potential, and the kinetic energy of the system put together is nothing but its internal energy. Yeah, but what is the physical significance of this heat and work? So heat and work can be called as the energies in transit. So they are also a form of energy, but they are energies in transit. Then how are they different from one another? Heat is one random movement of the energy. That means heat has got no direction. Heat is, that means when molecules are moving randomly in a disordered way, okay, without having any proper direction, then you say that form of energy in transit is called heat. But if the energy transferred is a very directional, okay, because when a system is doing work, that means the molecules are directed towards one particular way, right? So the directional form of the transfer of energy or that energy is called work. Okay, so that is the difference between, if you look into the molecular level, what is the difference between heat and work? A disordered movement of the molecules without any direction, that gives rise to heat, whereas a directional one, the transit, it is giving rise to work. Okay. Of course, heat content or enthalpy. First law also introduced this term known as enthalpy, or the heat content of the system. Okay, which is represented by H. Okay. So what is this? This is nothing but related to the heat liberated or heat absorbed, the heat content or the enthalpy. It is related to. So delta H, or change in enthalpy, is corresponding to the amount of heat which is absorbed or evolved during the chemical reaction. So, excuse me. Yeah. Then other terms, that is heat capacity. What is heat capacity? Defined as the amount of heat required to raise the temperature of a substance to 1 degree centigrade is heat capacity. If you are defining it for 1 gram of a system, it is specific heat capacity. If you are defining it for 1 mole of the substance, it becomes the molar heat capacity. You also have the latent heat. This is the heat required to change the state of one unit of a mass of a substance at constant temperature and pressure. Okay, so when there's a phase change involved, so that heat required during the process, it is known as the latent heat. And of course, depending upon the physical process, you can have latent heat of fusion, latent heat of vaporization, etc. If the process is a fusion process, freezing of the substance is taking place, then it is heat of fusion. Vaporization is taking place, it is heat of vaporization. Okay. Yes, this is more about the heat and work. So we know that the heat and work are internally related, I mean convertible to one another. For example, the work done by gas, it can be a change in work, that is dW, it is given by, that is when a force is applied, there is a movement, there is a change, that is a volume, that is expansion or compression of the gas, there is a volume change taking place. That's why we say it is PdV, the work is, this is infinitesimally small change. That's why dW giving rise is because of the small change in the volume. On to the total work done, what is the total volume change? You have to integrate it. The limits are the system is going from a state of volume 1 V1 to V2. So therefore W is integral of V1 to V2 PdV. So we get that P into V2 minus V1 we will be actually getting, right? Of course, the sign I already told you about the that is whether it's a work is done by the system or on the system. Based on that, the sign of it depends. And then I already talked about the various thermodynamic processes, that reversible, irreversible, isobaric, isochoric, etc. We can also have what are known as cyclic process. What is a cyclic process? When the initial and the final state is the same. That means a system is going from a state, say 1, and again it is returning after a process, it is returning back to the same state. It's called a cyclic process. As you can see, and the name indicates cycle. So you know that in a cyclic process, there is no change in the internal energy taking place because initial and final states are the same here. Therefore, the dE or du is 0. There is no change in the internal energy taking place in this cyclic process. Okay. Also have some quasi-static processes. Excuse me. That is a very slow process and the system is always maintained in the thermal equilibrium. It's called a quasi-static process. So work done for various types of process we are discussing here. So based on this, okay, always work done in a reversible process is much greater than the irreversible process. Okay, as I said, reversible process, what is happening? Slowly, infinitesimally small changes have to take place that add up together. So therefore, it's not a sudden change. It has to take place with a small, infinitesimally small steps are involved in that if reversibility has to be taken. So always work done in a reversible process is greater than an irreversible process. So these are all the mathematical expressions used to determine the work. This is for an isothermal process. So if you know the volume change or the pressure change, you can always determine the work done in a system using this expression nRT log V2 by V1 or P2 by V1. How did we get this? You have seen that P delta V, right? From that only actually you got this expression. And if it is an adiabatic process slightly different, right? There is no heat change taking place. So the work done is given by this expression nR T2 minus T. That means it depends on the temperatures. See, please, you have to understand when you're talking about the adiabatic process, no heat change doesn't mean that the temperature is not changing. Temperature, for example, the best example, what do you give for an adiabatic system? Like, you know, when there is no heat change, you take, there is no exchange of heat, but the temperature is not remaining constant there. Temperature is changing, okay? So that's why What is the variable here? Temperature is changing, but heat is not changing. Divided by gamma minus. What is this gamma? Gamma is the ratio of the heat capacities. That is heat capacity at constant pressure to constant volume, right? This is Cp by Cv is known as gamma. Okay. Yeah. And you can prove that that's Cp minus Cv is equal to R, the gas constant R. And what are the other expressions used in adiabatic process is you have PV is equal to constant for a normal process, but in an adiabatic process it is PV raised to the power gamma constant, or TV raised to the power gamma minus 1 is constant. So you can actually in your syllabus I think you have the derivation also for this. Prove that PV raised to the power gamma is Cp minus Cv, how it is R is also is shown here from the expressions. I'm not going into details of this. These are the various PV diagrams, the isocores, isobars, isotherms, etc. Okay, so here no, both are not isocore. Please, I'm sorry here. This is one is the second one is the isobaric process. The first one is isocoric. That means volume is constant, the pressure is changing. Can you see here the vertical line? The second one is, sorry, this is not isocoric. What it should be? It should be an isobaric process, right? Excuse me. One second. Jyoti, did you disable annotation?
Ma'am, annotations, ma'am. I think it is like you can use, I think, ma'am.
No, but I'm unable to see here. That's why. I thought, did you disable or something? Unable to see annotations here. Did you disable?
Actually, the
well, okay. I just wanted to use the pointer there. That's why. Okay, leave it. The second one, please make a note. This is an isobaric process because you can see the pressure is constant. Y-axis, the value P is constant. So it's an isobaric process. Isothermal process, you can see here, and the adiabatic. So can you compare? If you just see that the area under the curve, if you this is the you will get the work, the pressure volume work. You get if you measure the area under this curve, you will be getting the pressure volume work. So always the work done in a adiabatic process is lower than that of this dotted line is the isothermal process, and the this curve is the adiabatic. If you see the area under this curve is smaller than the total area under the dotted line. So always the work done in an isothermal process is much lower than that in the adiabatic process. So these are the various expressions that we use for the pressure and volume and the work done, heat capacities, etc. and all that. Just summarized in one table. Yeah, this is what I was talking about, the isothermal reverse. This is isothermal reversible and irreversible expansions. I told you the work done in a reversible process is always greater as compared to the irreversible process. So you just can see this is the work done in the irreversible process, the which is indicated in this rectangle. So if you compare the areas, you can see that always in a irreversible expansion or compression process, the work done is greater. This is showing adiabatic and the isothermal process. This also I already told you. Yeah, the principles of first of thermodynamics also applied and in liquefaction of gases. I think you have read this in your gaseous state also, I think, right? Based on what is known as Joule-Thomson effect. If you want to liquefy gas, that means what do? You have to cool down it, right? So, or apply pressure. These are the two means. How do you get a liquid out of a gas? You have to bring down the temperature, cool down it, or you have to pressurize it. So apply pressure, then the gas will come to liquid state, right? But you know there are certain, the real gases are not very easily liquefiable. There are some gases which can be easily liquefiable. The other gases, based on what is known as their critical temperatures, they cannot be easily liquefied. They're using this Joule-Thomson effect, which is based on the first of thermodynamic, the principles. You can see the various gases here. You can see the hydrogen and helium, they're very, very difficult to cool down. You have to go to minus 200 degrees, below minus 200, 250 degrees centigrade if you have to get liquid hydrogen or liquid helium. Whereas carbon dioxide, it is much easier to liquefy. So they're using this principle of Joule-Thomson effect. What is that Joule-Thomson effect? It says that if a gas is compressed suddenly, allowed to pass through a porous material, okay, then the gas starts cooling. So it is cooled adiabatically. That means there should not be any exchange of heat taking place. If it is gas is adiabatically, compressed. So what happens there? I'm really sorry. The compressed gas is adiabatically made to expand. That means that from high pressure to low pressure. So when it is moving through this porous material, here it is compressed, the gas, it is made to move into this low pressure area. That is, it is made to expand. What happens? Adiabatically, that means there is no heat exchange taking place. Then the gas is accompanied by cooling, starts cooling. So it's by adiabatic cooling that is taking place. The gases gets liquefied. So applying, this is known as the Joule-Thomson effect. So most gases at one particular temperature, they start cooling down. Unlike some gases like helium and hydrogen, they show heating effect. That means they don't get cold, they get heated. That is because it depends on what is known as the inversion temperature. The inversion temperature, that means if the gases are cooled beyond the inversion temperature, they undergo, they are made to expand beyond the inversion temperature, they experience cooling effect. Okay, but below that inversion temperature, they show the heating effect. So that's why it's called the inversion temperature. At that above that temperature, they show heating effect. Below that temperature, they show the cooling effect. The inversion why this hydrogen and helium, they are showing even on adiabatic expansion, they are showing the heating effect, is that the inversion temperature itself is very, very, very low. That is minus 240, 250. If you, it is minus 240 something for helium. So unless you go to that temperature, that means you are trying to cooling it to minus 100, still it will undergo only heating effect, but will not show the cooling effect. So that's why it's called the inversion temperature. The behavior of the gas is showing an inverse behavior. That's why it's called an inversion temperature. So the liquefaction of gases is based on this Joule-Thomson effect, right? Yes. So this is the Joule-Thomson coefficient, which is given by dou T by dou P. That is this dou T by dou P. That means when you're releasing, that is decreasing the pressure, the temperature is falling. That is dou T by dou P. This Joule-Thomson coefficient is either positive or negative based on the inversion temperature. Below inversion temperature, it's positive. The above inversion temperature, it is negative. That's what. If it is positive, means it's showing cooling effect. It is negative, means it's showing a warming effect. That's what is meant by this. Of course, this whole lot of what is known as thermochemistry is again based on this enthalpy, that is enthalpy of physical process, enthalpy of chemical process you will study. Enthalpy is the heat change involved when there is a phase transformation occurring with respect to materials, or there is any chemical reaction taking place. So what is enthalpy? That means it is the heat content. The reactants have got certain heat content. When they transform to products, they have a different heat content. This difference in the enthalpies, the heat contents of the reactants and the product, this difference is known as the enthalpy of the reaction, delta H. Delta H is nothing but the summation of all the, you may have more than one product, more than one reactant. So summation of the enthalpies of all the products minus, always final minus initial, right? Change is always final minus initial. So the summation of all the product enthalpies of the products minus that of the reactants, that will give rise to the total enthalpy change involved in a reaction. Now here it comes this delta H. If it is greater than 0, it's an endothermic process. That means the enthalpies of the products is greater than that of the reactants. It's an endothermic process. If it is the other way, that is the enthalpy of the reactants is greater than the products, then it is an exothermic process, right? So based on that, heat is absorbed or heat is emitted out. So it shows, it is based on this Hess law. What it says that if a process occurs in stages or steps, okay, the enthalpy change of the overall reaction is net sum of all the enthalpy change of the individual steps. That means the reaction may happen in one or more than one step. So then the total enthalpy of the process is nothing but addition or summation of this. That means one step may be exothermic, the second step may be endothermic, right? For example, you're getting a product P from A, okay, or A plus B is giving you the product C plus D. So in that process, again, first A is transformed to some A prime, then B is transformed to B prime, then again B prime is A prime is transformed to C, B prime is transformed to D, like that. You know, there are several steps involved. So you don't have a single step or a one just elementary step involved in a reaction. Reactions are very, very complex in nature. They involve multiple steps. So when you consider all the different steps, one step may be one process may be one step may be an exothermic process, the second may be endo. So like that, adding up all the endo, exo, all these steps, the total enthalpy of the reaction is determined by all these steps involved. That's what is stated by the Hess law. Okay. And then you also have the Kirchhoffs equations relating this delta H with respect to that of the heat capacities and temperature. Okay, so this is what that is delta H2 minus delta H1 of a reaction. That means at two different temperatures, you will have two different delta H values. That is when you vary the temperatures of the reaction, the delta H reactions keep varying. So this change in the delta H value from T1 to T2 is equal to integral of T1 to T2 between the limits T1 to T2 delta Cp dt. Okay, so you have the Kirchhoffs equation, which is relating to enthalpies with the temperatures and the heat capacity at constant pressure. Okay, that means what? If you know the enthalpy at one particular reaction, and one particular temperature, you can determine the enthalpy of the system at another temperature, always using this reaction, equation. Yes, so we talked about a lot about this first law of thermodynamics. See the process here, if you look into this, what is there? You have two different gases separated by a diaphragm. If you remove, spontaneously they start mixing up. You have a balloon with gas filled. If you release that knot easily, the gas, which is escapes out. So the inflation of the balloon is lost. Now its volume is decreased. Similarly here, when you are dropping a weight, it spontaneously it is falling here. You have a hot coffee mug. If you leave it like that, what happens after some time? All the heat is lost. So what are all these processes? These are all spontaneous in nature. They're happening on their own. But if we just look into the reverse, can it happen? The gases which mixed up like that, you know, the red balls and the blue balls, can they again come back to themselves, you know, when you put the diaphragm, you know, easily separating off into blue and red, or the one which is lost on itself come back to this pressurized state of the balloon, or the weight that is dropped, can it go back to this position on the hook? It can, or the one which is lost, we can, it take heat itself, go into a hot, and that is cold coffee, can itself become a hot coffee without an external agency? No. So what we talked about, the heat transfers, work done, and all those things, enthalpy, etc., and all that. Yes, no, correct. So I think what you said is right. No, it cannot happen. That is what is the non-spontaneous process. That means what? Your first law of thermodynamics is, it's telling you about the work energy relationship, how work can be converted into energy, energy can be converted into work, etc., and what is the enthalpy of the system, how you calculate all those things. But it is not talking about why cold body cannot get heated up, okay, on its own, or this processes, you know, why it cannot happen the other way. That means the direction of flow of the heat or the energy is not, the kind of information is not obtained from the first law of thermodynamics. Why this is spontaneous, the other one is not spontaneous, you don't understand from the first law of them. Those, so there are certain limitations associated with the first law of thermodynamics. So no restriction on the direction of flow of heat, doesn't give any information, doesn't talk about the feasibility of the reaction, why only this process is happening, the not the other process. Okay, about the feasibility of the reaction, what is the quantity which determines the feasibility of the reaction. And practically it's not possible if you're saying there is a mechanical equivalence of heat to work, but practically when you see 100% heat can never be converted into work, or work can never be totally converted into heat. This kind of what is known as total equivalence is not there. So this has given rise to, or this has given the necessity for the second law of thermodynamics. So that's how second law of thermodynamics came out, with the limitations of the first law of thermodynamics. There is no single simple statement for second law of thermodynamics. There are several statements given by Cauchy, Kelvin, and Planck, and you also have the one statement which is related to entropy. So this is one interesting quote that I wanted to say. He is relating it to our day-to-day life. That's Seth Lloyd. He says, nothing in life is certain except death, taxes, and second law of thermodynamics. So only thing in the world is what we are certain about is the death, which is the natural process. Everything which is living has to die. And it seems everybody must and should, we cannot go away with the taxes. And of course, second law, it's such a definite thing, he says. So the Cauchy, as per the Cauchy statement, he says, it's impossible to construct a device as heat pump that operates in a cycle and produces no effect other than transfer of heat from low temperature to higher temperature. So that means what? That means from hot reservoir to cold reservoir, the heat can be transferred, but from cold to hot, it can never happen. Cold body can never, the heat cannot be carried from cold body to a hot body, right? So this is just wanted to show, I've seen, I got it on the internet. This is a memorial stone in Koszalin University of Technology of Cauchy. They have kept this memorial stone of Cauchy, who is the one proposed this second law of thermodynamics. He formulated the second law of thermodynamics. The other statement given by Lord Kelvin and Planck. So what it says is, it is impossible for any device as heat engine that operates on cycle to receive heat from a single reservoir and produce any net amount of work. So this is another way of stating the same thing, right? it's saying that the total heat absorbed by heat engine from a high temperature is converted into work, and the remaining heat must be rejected at lunch. That means what? Totally 100% heat cannot be transferred in the performance of the work. Always there is some amount of heat lost. So that is what the Kelvin Planck statement. So there are other forms of statements also given. So there's no heat engine can have a thermal efficiency, 100% efficiency, they said. Entropy statement, what it says, that the total entropy of any system. So we have not defined entropy. We will define this. This is the concept that has come out of this second law of thermodynamics. They said entropy of a system plus its environment always increases in a natural process, or entropy of the universe is continuously increasing. Natural processes tend to move towards a state of disorderness. So entropy is, what is entropy? Entropy is the disorderness or randomness of a system. So the measure of randomness or disorderness of a system is entropy. Okay, it is related to various modes of motion in molecules. That is, molecules, they're moving, they exhibit translational, vibrational, rotational movements. That is, whenever the molecule is making a movement, it is accompanied by an entropy change. So if it is going from a more disordered state to an ordered state, it is accompanied by decrease in entropy. But when a system is going from an ordered state to a more disordered state, it's always accompanied by an increase in entropy. So delta S is always for a natural process or a spontaneous process, right? It is mostly positive in nature. That is, always a spontaneous process goes towards the increase in the entropy. Now, how did actually this term entropy come into picture? It is mathematically given by delta Q by T. Okay, you know that Q is, that is heat, is a path function. What they have observed is, when this ratio of Q by T, when you do it, they observed that this quantity has become a state function. Okay, so yeah, talking about this thermal equilibrium, what is said in a reversible process, it is always actually, we have to actually write it as Q reversible. Delta S is equal to delta Q reversible by T. Okay. Yes. So I just now told about this. This Q by T, this quantity, when they have observed, this is HC means hot body and a cold body. When its heat is transferred from hot body to cold body, what they observed is this Q by T of C, that is cold body, is greater than the Q by T of the hot body, because always the temperature of the cold body is less than this. So when you take this total, this content, they have observed it to be equal to greater than 0. That means this delta S, which is Q by T, they observed it to be positive, greater than 0. That is, change of entropy gives the direction of the process. That means a spontaneous or non-spontaneous process can be determined by this quantity of delta S. There we have also seen, in case of delta H also gives certain information. There's exothermic, endothermic process, because exothermic is a spontaneous, but because itself is giving out energy and coming, but if it has to acquire energy for any process, it's, it is not spontaneous in nature most of the time, right? Delta S also, that is, sorry, delta H also, you can talk about the spontaneity. You can say that exothermic processes are spontaneous, whereas endothermic processes are non-spontaneous. Even delta S is one term. It talks about the direction of the energy dispersion. It says delta S is positive, always goes towards increase for a spontaneous or a process. So for example, here, I'm talking about a glass of cold water is placed in hot room. Consider small amount of heat change, that is delta Q. So which of the statements of here is true? Delta is, is greater than 0, or is it less than 0? When you're considering you have to consider both. See, what entropy of water, entropy of the room. What happens to the entropy of water? it's a glass of cold water, right? So it is taking heat from the room. So then what is happening? The entropy change with respect to water is greater than zero. It is moving towards increase. When you considering that of the entropy of the room, because it is giving heat to the cold body, losing heat, right? So delta Q is less than zero. So here the entropy of the room is less than zero. This is decreasing. Whereas entropy of water, it is increasing. So, but overall is the combination of these two. That means system as well as the environment put together in most natural or spontaneous or irreversible process, it goes towards the increase. That's why we say entropy of the universe is in general is increasing. Yes. This is just now I said about the reversible and irreversible. So for a reversible, the entropy remains constant, because whereas in irreversible process, it's always accompanied by an increase in the entropy of the universe. Okay. And if there is no heat change taking place, zero, then delta S is zero. That is nothing but a adiabatic process. So adiabatic process, we can also call it as an isoentropic process, because there is no entropy change in an adiabatic process, right? So therefore adiabatic, we know that isobaric process, pressure is constant, isochoric volume is isothermal, T is. So we can say adiabatic process and isoentropic, that means constant entropy delta. Yes, talking about this reversibility or irreversibility of the system, the statement given by Cauchy's inequality, change is greater than zero under irreversible conditions, but under reversible conditions it is zero. That's what just now we talked about. Delta S is zero for a reversible system, whereas greater than zero for a reversible. So put together you can say delta S is greater than or equal to zero. Okay, so this actually talks about the process inequality. Okay, but this inequality shows as if, you know, entropy is not a state function, okay, because it is different for reversible and inversion. But we know that entropy is a state function. How this contradiction is seen is, if you see the system alone, it appears as though it is not a state function. But if you put it together, because delta S is nothing but system plus the surroundings, when you take it in a holistic way put together, then you can say that this statement is not false. It is holding good, and it is also satisfying that delta S is a state function. So this is the Cauchy's statement showing, you know, for a biological system, you can say in the cell also, it is always, there is an increase in the entropy taking place continuously. There is several metabolic processes taking place over there. The cell, new cells are developed, these cells, they die out, right? So, yeah, put together, you can say, always, yeah. One more important thing I wanted to tell you is, you know, when you say mathematically a system is state function, you have three mathematical conditions. You can say that there it is an exact differential, okay, and the double differential with respect to two different variables should be equivalent. And when you do a cyclic integral, if it's a state function, what happens? Initial and final state is the same. So therefore, a cyclic integral always is equal to zero. This symbol, it indicates the cyclic integral. This circle, what you are showing for the integral, indicates that the initial and the final states are the same, the cyclic integral. So for a reversible process, this quantity delta S is zero, less than zero for a delta Q by T is less than zero for irreversible process. This cyclic integral of dou Q by T is greater than zero, which is impossible condition. So that's why Cauchy's statement always says it's greater than or equal to zero. Okay. Yeah, but there is much more with respect to this entropy. The physical significance of entropy is not just talking about the randomness of the system. The physical significance is something else. When you talk in terms of actually this branch of thermodynamics, which deals with the what is known as microscopic properties of the thermodynamics, is statistical thermodynamics. So as the name indicates, statistics, because thermodynamic, it is always defined for the macroscopic systems, larger bodies, larger quantities. But thermodynamics has got no as such, the relation with the molecular scale properties, that is microscopic properties you cannot relate exactly in that. So there is one link which actually links up the microscopic properties, or microscopically you can link to the molecular states, atomic states, is through the statistical thermodynamics. So as the name indicates, statistics means always number, quantity. So here actually you're talking about thermodynamics is the energy of the system is so and so. So it is changing from this energy to this temperature to this. But how many molecules are actually possessing that energy? Out of 100 molecules, all molecules will not be having the same amount of energy. Each set of molecules, there are 10 molecules having 10 calories, 20 molecules may be having 20 calories, like that. So energy distribution is not the same, but we are taking the overall, right? So when it's changing, what is actually happening in the molecular scale, we do not know, or how many. So this statistical thermodynamics is one which links up, talks about the energy states, how many molecules are having this energy, and when what energy state to another energy state it is moving when there's temperature changes occurring or volume changes occurring. So this kind of, and it also relates to what is known as the microstates. Microstates are a configuration. What do you mean by that, microstate? For example, you have 4 particles, say A, B, C, D. These 4 particles, you have to say 2 compartments here. Okay, 2 cubicles. All the 4 can exist in one of the cubicle. This is one particular configuration. You can arrange the 4 particles. Or you can arrange this way, 3 B, C, D in one, A in one. So only one particle in the second compartment if you have to place, any 3 of it. So how many possibilities are there? There are 4 possibilities. They are called the 4 microstates with 3 particles on the left and 1 on the right. Or 2 if you have to place. Like this you can have. How many? 6 microstates are possible. So these are all the possible arrangements, possible states. Those are called the microstates. So within a particular state, and particular energy state can have all these microstates when you talk in terms of individual particles or the molecules or atoms, right? So these are called the microstates. Now, whichever is the most probable state, okay, that will determine the condition of the system, okay. So that is nothing but the probability. So when you can also talk in terms of that is known as probability. That means when you toss a coin, for example, here, yeah, let us complete with this microstate. The possibility of finding all 4 particles on the left, it is only 1/16. So you have seen there only one microstate is possible. All the 3 it is, you have 4 states, microstates. So 4 by total configurations are 16, right? So 4 by 16 you have. Finding 2 particles on the left, you have 6 by 16. So what is happening here, when you're giving the possibility of the particle being in any particular state, the probability is increasing here. When you're saying all the 4 in, that means the possibility you are limiting to one particular state, right? So this is all the 4 should be on the left, we are saying. So then the probability becomes less. This is very easy if you want to understand in terms of tossing the coin. We always explain the probability. Now, when you toss one coin, there is always equal probability of the head or tail to be. That means you have 2 states, either the coin being in the head form or in the tail form. So 50-50%, 1 by 2, 1 by 2, right? But if you're tossing 2 coins, You say one head, one tail, that means the possibility is first one head, second one tail, or second one head, first one tail, right? The probability is again the same, but if you are specifying that both should be head, when you're tossing two coins, what is the probability? First one head, second one tail. So other possibility is first one tail, second one head, both tail, both heads. So 4 possibilities are there, but you are specifying that both should be head. And what is the probability? 1/4. So it is smaller. But if you're saying one is head and one is tail, you're not specifying. There are 2 states possible. The probability is now 50%, 2/4, right? So we're talking about the states which are more disordered are more likely to happen. Any system means more disorder, any form. You are not specifying that. When you're specifying one particular state means you're defining the orderedness of that. So always more disorderedness is more likely to happen, more probable. More disorderedness is associated with more probability. Okay. See, it is so difficult when you're talking about only these 4 particles. We're talking about atoms in 10 power 23, Avogadro number. What it is, it's much more greater, right? So, in terms of these microstates and probability, you can define the entropy given by this microscopic expression S is equal to K log W. Now, this W is the microstates. Greater are the microstates possible for that particular configuration, then the S is the greater value. Okay, so the probability is greater is the disorderness or entropy of that particular system. Okay.
Excuse me, ma'am.
Yeah. Yeah, please. Hello?
Sindhu, you can ask question after the lecture.
Okay, ma'am.
She has reached out. She wants to ask something.
I think, ma'am. Yes, ma'am.
Ma'am, actually the question, not the question, ma'am. Actually, little confusion about that probability. So, thought of like a quick reference, ma'am.
Yeah, I was talking about tossing the coins. Did you understand that?
Yes, ma'am.
Or these configurations I've given you the example, the particles. See? So when you're specifying that all the 4 particles should be only to the left, that means it's a more specific or more ordered state, is it not? So what is the probability of this state being existing out of all the 16 states? It is 1/16. The probability of this event happening is least 1/16. But if you just say, any 2 particles onto the left, then how many possibilities are there? You have 6 possibilities. 6 microstates are possible. That is 6/16. The probability has increased, no? Isn't it? So that event to happen, see, this event is difficult. I told you about the coins. When you toss 2 coins, you want both the coins to have head. The possibility of both the coins to have head is only 25%, because 1/4 of the total 4 possible events or possible states. But you say 1 head and 1 tail. That means you're not specifying which coin should be head, which coin should be tail. Okay, so then you can have first one head and second one tail, or second one head, first one tail. There are 2 possibilities there out of 4 possibilities. So 2/4 means half. So there is 50% probability. So is it not more probable? So that event to happen is more probable, right? So greater is the probability of any system, greater is the disorderness. When you're specifying that the system should be of certain configuration, that means what you're limiting its probability. Therefore, the disorderness of that system is lower. So whenever you're tossing any event is happening, so you're not restricting the event, or anything can happen. When you're saying anything can happen, that means the probability is greater, no? So when you're throwing, say, the what do you call? You use this what is known as shells, no, for playing this games, Ludo and all that, right? There also no dice when you're throwing. So any, say, getting any one particular value is always more probable than you say, I want only 6 for the dice. What is the possibility of you getting the dice only 6? It is very less, right? So that is what is happening. That means a more ordered system. So what is the physical significance of entropy? The more probable a process is, more disorderness is associated, because the processes in nature, or most processes, they tend towards disorderness in the universe. So that is what I'm trying to link up here. The entropy, the physical significance, you have to understand in terms of the probability of the system. Okay, so that's what this relation it gives, that equation S is equal to K log W. This W indicates the possible microstates. Okay, am I clear?
Yes, ma'am.
Yeah, we talked about entropy being a state function. This is what it shows. You can prove that it is state function when you prove that this cyclic integral is 0. Okay. Yes. What is the? This is the most important part of the second law of thermodynamics, because this is given by Sadi Carnot. So he's actually considered as the father of thermodynamics, because thermodynamic application goes much more with the engines, motors, rockets, anything you name, any machine, any engine, it works on the principles of thermodynamics. So he is the one first who applied this second law of thermodynamics in understanding the efficiencies of the engine. As per the Carnot's theorem, it states, no heat engine working in a cycle between two constant temperature reservoirs can be more efficient than a reversible engine working between the same reservoirs. So that means what? One second. Excuse me. Yeah. So talks in terms of this Carnot's, yeah, terms of the Carnot cycle, which describes the efficiency of an engine. So the engine which is working on, through this Carnot cycle shows the maximum efficiency. What is efficiency of an engine? Efficiency of engine is given in terms of W by Q. Okay, that means work done using the heat, or work work done on the system by using the heat, or work done by the system giving out heat, whatever it is. Okay, the W by Q, the work performed by the engine depends, the efficiency depends upon the work done and the heat involved. Or you can also write it as the heat between the hot and the cold bodies, QH minus U, this heat difference, because that heat difference is required. If you have to, the system has to perform work, there should be a hot body and a cold, that's a reservoir and a sink. Okay, so reservoir is a hot body, sink is a cold body, QH minus QC. Greater is this difference between the reservoir and the sink, the greater will be the efficiency of it. That means if you have one is working, the heat involved should be, this difference should be greater. That you can also write it in terms of the temperatures. This is given as T2 minus T1 by T1. So greater is the temperature difference, greater will be the efficiency of that engine. Now you can prove that the maximum efficiency of an engine can be obtained through this Carnot cycle, which involves, it's a 4 strokes. That means 4 processes involving 2 isothermal process, 2 adiabatic process. So from 1 to this 2 first, there is accompanied by isothermal expansion followed by adiabatic expansion, then isothermal compression followed by adiabatic compression. So from this, how did you get this expression, this 1 minus Tc by Th? That's what I said. You got it from this Carnot cycle, applying these expressions for the isothermal and the adiabatic process. I'm not going in detail with this because of the time limitation. You can see this derivation here. Right. So that's what I said. Greater is the temperature difference, greater will be the efficiency of it. So maximum, because this is involving the reversible process, that is isothermal expansion, compression, adiabatic expansion and compression. So maximum efficiency of engine can be attained by this reversible cycle. If you're not performing a reversible cycle, you can, that means this statement says, yes, the maximum efficiency is obtained with a reversible engine, not the one, if this reversibility is not maintained, you don't get the maximum efficiency. Excuse me. This is that 4 strokes. See how the engine is moving. First, it's made to isothermally expand, then adiabatically, then isothermally compressed and adiabatically compressed. So this is 4 strokes. Okay. Yeah, these are all the various expressions you can have for entropy. For an adiabatic process, so it's 0. For isothermal process is given by delta S is equal to delta Q by T. If there is any phase change taking place, okay, that is phase transformation, it is given in terms of the latent heat of transformation at that particular temperature. Okay, and isobaric process, you have the expression, yes, and yes, this the entropy of a gas can be calculated, that is delta S, using the it can be a volume change or a pressure change. You can determine it as CV log T2 by T1 or log V2 by V1, or if 2 temperatures are given and you know that pressures correspondingly, also you can find out the entropy change. Okay. When you have gases, mixture of gases, ideal gases, if they are mixture of ideal gases, when 2 gases are allowed to mix, the delta S mix change, it is given by minus R XA log XA plus XB log XB. This X is nothing but the mole fraction of that particular gas. Okay, so this value is always positive, that is spontaneously when 2 gases are allowed to mix, it is accompanied by a entropy increase, right? Yes, I told you delta H and delta S values, they give the information with regard to the spontaneity. So I told you that exothermic reactions are spontaneous and delta S positive also spontaneous. But there are certain reactions, for example, if you see delta H is positive and delta S is positive both, but still the process is spontaneous. For example, this is an endothermic process, that is when there is the ice, it is kept outside, it's taking heat in, that's melting, right? It's taking in heat, melting, but it's still spontaneous in nature. Similarly, if you take adsorption process, adsorption is a here what is it? Delta S, delta H, delta S both are positive but still spontaneous. In this case of adsorption, what is adsorption? Adsorption is sticking of the atoms and the molecules onto the surface. So how are they sticking? Through some van der Waals interactions there. That means the molecules, they are binding to the molecules on the surface of any substance which is known as an adsorbent, okay, through some weak van der Waals physical interaction, that is weak van der Waals force of interaction, that is physisorption, or they can really have some kind of chemical interaction, chemical bonding, that's called chemisorption. Okay, whenever this adsorption is taking place, what is happening to the entropy of the system? There is a decrease in the entropy because the freely moving atoms are now being bound to the surface. So the entropy has decreased. It's gone to a more ordered state. But this is an exothermic process. Adsorption involves release of heat. So both delta S is negative and delta H is negative. So you can see these are the classic examples where, the delta S alone or delta H alone, they fail to speak about the spontaneity or the feasibility of the process. We said all exothermic, if you consider only enthalpy, all exothermic should be feasible, spontaneous, and all endothermic should be non-spontaneous or non-feasible. Similarly, delta S is positive, all processes are feasible. Delta S is negative, all those processes where delta S is negative should be non-feasible. But it is not so. That's what you have seen these two examples. So therefore, a new thermodynamic variable was required, thermodynamic entity or property.
Ma'am, you are on mute, ma'am. Please unmute.
Oh, how long have been? I'm sorry.
2 seconds back, ma'am.
Okay. So where did I think these two classic examples I was telling about.
This completed, ma'am.
Yeah. So that's why it has given rise to. I mean, there was a new thermodynamic property required to determine the feasibility, talk about the feasibility or spontaneities of the reaction. That's what are these functions known as the Gibbs energy, the free energy functions, Gibbs free energy and the Helmholtz free energy came into picture, right? So the Helmholtz free energy is represented by A, Gibbs free energy is represented as G. This is a constant temperature volume process, constant temperature pressure process. It is the Gibbs free energy. Okay, so I'll directly go to the equations. Yes, the Helmholtz free energy is given as E minus Ts or U minus Ts. Okay, a combination of the internal energy and entropy is called the function, which is called the Helmholtz free energy. So it's isothermal isochoric process combined together. Okay, here. Okay, this is also known as the work function because this is directly related. The physical significance of the Helmholtz free energy is that the Helmholtz free energy delta A decreases. It's a spontaneous process and it's a minimum at equilibrium. Okay, when two processes are at equilibrium. Why is it called the work function? Is that if you try to expand this, okay, U minus Ts, no? So du is equal to minus PdV plus TdS. So this is accompanied, that means change in Helmholtz free energy in an isothermal process. Suppose this T is kept constant, it is nothing but this PdV, it gives equal to minus PdV. So, this is called the total work function because this directly gives information regarding the work done by the system. So delta A, the total Gibbs free energy change, Helmholtz free energy change is equated to reversible work done. Now, actually, this A, why is it represented as A? A means Arbeit. That means work in German. That's why it's represented as work. And why is it called the free energy? Because it is the energy done by the free system. There is also one bound energy because if you take U as equal to, A is equal to U minus Ts or U is equal to A plus Ts. That means internal energy is equal to this free energy A plus Ts. Ts is the bound energy which cannot be converted into work. There is some amount of work energy which cannot be converted into work. This is the energy which is available with the system that can be converted into work. That's why it's called the free energy. You got this equation, right? A is equal to U minus Ts. So U is nothing but A plus Ts. So the total energy, internal energy of the system is this free energy plus the bound energy. Okay. So that's why A is called the work function. And G, it is given by H minus Ts or delta G is equal to delta H minus T delta S. Okay. I'm going a little faster. See this. So this delta G represents any other work other than PV, the pressure volume work. So it's also called the meaningful work. Okay. So delta G it's also known as the meaningful work. In a closed system of constant temperature and pressure, if no other than PV work is done, the Gibbs free energy decreases in a spontaneous process and it is minimum at equilibrium. Same thing. So any spontaneous process, delta G should be negative, or even for Helmholtz free energy, it should be negative. For an equilibrium process, it is minimum. Delta G or delta H A values should be minimum. Okay. These are the relationship, the equations relating G and A. So that's what I said. Other than the PV work, non-PV work, it defined as the non-PV work. And the changing this Gibbs free energy with respect to composition, because see here we are not discussing the non-equilibrium systems. We are all the time here we are discussing the equilibrium. That means what? We are only considering the processes where there is no change in the chemical compositions of the system. We are not considering chemical composition. We are always considering what? Change in temperature, change in volume, change in pressure and all. We have not considered other variable, which is the composition. Composition of the system also can change, right? When you're taking different substances, it is not the same. The composition during the process, it is not the same. Each you have two or more components, each one will have different compositions. So this Gibbs free energy keep changing with the composition also. That's in a non-equilibrium process. They also keep changing. So this quantity is known as the chemical potential of the system. That is change in Gibbs free energy with respect to composition, okay, of the components with pressure, temperature or volume. These other things remaining constant. So this quantity is called the chemical potential of the system. Okay. And yeah, these are the you can represent in this bar. See the different thermodynamic functions. You know this H, enthalpy is the largest of all these. This is the G, the contribution from G. It is the non-PV work. What you said. A is the work function, and U is the internal energy. So when you compare all the four thermodynamic functions, A is the least, then G, that is Gibbs free energy, U, and highest will be the H, that is the enthalpy. Yeah, this is the, when you describe, that means this Gibbs free energy is put forward to explain the spontaneity or feasibility of the reaction as a combination of this delta S and delta G. So yes, for a spontaneous process, delta S is greater than 0, but delta G should be less than 0. Okay. And a process which is accompanied by delta G less than 0 is known as that is delta G is negative. It is known as an exergonic process, where delta G is positive is known as an endergonic process. Okay. And for equilibrium systems, the delta G is 0. Yes, this is important. The significance of delta G, that means it is a combination of delta H and delta S, we said. So it is understood at low temperatures. It is delta H is exothermic. Okay, that is delta H is negative, and delta S, even if it is negative, if T is small, what happens? If T is small, even this is negative, what happens? This delta H sign will dominate. The overall delta G will be negative. So it can be a spontaneous process. Or you can have delta H is endothermic, delta H positive, delta S is negative. Okay. So at any temperature you take, always this becomes a non-spontaneous, high or low. What happens always? This delta G will be a positive quantity, because delta S is negative, no? The overall this becomes plus delta H plus T delta S. Delta H is positive, this T delta S is also positive, total is positive. So at any particular temperature, if delta H is positive, that is an endothermic process accompanied by a decrease in entropy, it is always a non-spontaneous process, cannot happen on its own. If it is an exothermic process, delta H is negative, then delta S is positive. Always it is a spontaneous process, because this this sum, this total is always negative, right? But if this is an endothermic process and there is an increase in entropy change, unless this T is very large, this negative sign will not dominate because delta H is positive. Unless T is very large, the sign will not dominate as negative sign will not dominate. The total will not become negative. Therefore, only at high temperatures, when both are positive, it is spontaneous. Both are negative, can also be spontaneous at low temperatures. Okay. Delta H is positive, delta S is negative, always non-spontaneous. Delta H negative, delta S positive is always spontaneous. So this table, if you remember, that is very easy to understand the spontaneities of the. So many times they ask this question in the general exams and also competitive exams. The same thing I have represented with some examples here. Right? So both one is negative, one is positive. Delta S is that all temperatures, I said it's spontaneous. Example is this. What is this? Fermentation process. Okay. Sugars to alcohols. Then delta H is positive, delta S is negative. So always non-spontaneous, all temperatures, delta S is positive. This is this conversion of oxygen to ozone. Okay. And both are negative. Okay, it can be positive or negative, that is depending upon low temperature or high temperature. The example is this reaction of ammonia and carbon dioxide giving you urea. Okay, both are positive. It's non-spontaneous. That means only at low temperature this process can occur spontaneously, and it becomes non-spontaneous at high temperature. Same thing when both are positive. If you do this reaction at low temperatures, it is non-spontaneous. But if you give some temperature at high temperatures, if you do, it becomes negative or spontaneous. The reaction between barium hydroxide, this is 8H2O hydrated. So ammonium nitrate, when it reacts barium nitrate, it forms. This reaction is an example for this. Yeah, the same thing I have represented here, the other relationship what you have with delta G. When talking about the spontaneities or the equilibrium reactions, it is related to delta G and equilibrium constant as minus RT log K. Okay. And delta G for an electrochemical reaction, it is related as delta G is equal to minus NFE. E is the EMF of a cell. Okay. Yeah, these are for various processes. Delta E, how do you calculate for an isothermal process? Relationship between G and A. Yeah, this is another important equation known as the Gibbs-Helmholtz equation that gives you variation of the Gibbs free energy with respect to temperature and pressure. This equation, this is one form of Gibbs-Helmholtz equation. H is equal to G minus T into dou G by dou T at constant pressure. And this is another form of the Gibbs-Helmholtz equation. Dou delta G by T by dou T at constant pressure is equal to minus delta H by T square. There's a lot of significance associated with Gibbs-Helmholtz equation because this is applicable for several physical processes. Wherever there is a phase transformations taking place and all, there's always this Gibbs-Helmholtz equation is applied in obtaining the enthalpies of the reaction and all that. And then another important equations, what you have called the Maxwell's relations, they are obtained using this what is known as Euler's reciprocity rule. So you have a function, say Z, okay, thermodynamic function. It is dependent on two variables, X and Y. Now, this is another mathematical condition to call this Z, this function, to be exact differential when it satisfies this condition. That is, dou Z by dou X at constant Y dy plus dou Z by dou Y at constant X dy. If you can write it this way, or to differentiate this Z with respect to X, then differentiate with respect to Y, or Z with respect to Y first and differentiate with respect to X later. That means you have, say, for example, enthalpy. Enthalpy depends on temperature and volume, right? So you have dou square H by dou T dou V. That means you have first differentiated change, you have recorded the change in enthalpy, the change in temperature. Then that quantity again you measured the change in volume. That is dou square H by dou T by dou V. Or you do the reverse. First you have recorded the change in enthalpy with respect to change in volume. Then you have recorded the enthalpy with respect to change in temperature. That is dou square H by dou T dou V or dou square H by dou V dou T. If these two quantities, either way you differentiate, first T with respect to T, then V, with respect to V, then T. If you get this quantity to be equal, then you can say that the particular function is exact differential. I already told you cyclic integral, if you have equal to 0 is an exact differential, right? So these are all the various mathematical conditions to define the exactness of a function, okay? Whether it's an exact differential or not. Using this exact differential condition. Now what we said, so this is double differential. Now to make it easy, this dou z by dou x, I'm writing it as m. Dou z by dou y, I am writing it as n. So you can reduce this equation to dou z equal to m dx plus n dy. Then dou square z by dou x dou y is nothing but what? Dou m by dou y. And dou square z by dou y dou x is nothing but dou n by dou x. So if these quantities dou m by dou y is equal to dou n by dou x, then you can say that that particular function is an exact differential. So you can derive this Maxwell's relation for any equations. You have 4 Gibbs equations actually. So from that, so first one, say you have this first law of thermodynamics, you have dou E is d is equal to TdS minus PdV. From this, you can derive this particular Maxwell's relation. So what is this? This is simply in the form of dz is equal to mdx minus ndy. So here your z is u, m is s, and m is t, n is p, x is s, and y is v. Now just simply have to substitute dou m by dou x at y is equal to dou n by dou y at x. So simply what is m and s? Here I've written actually, see here. So this is your dou z. This is please this box is come in place of z. This is dz is equal to mdx plus ndy. So just simply you have to replace what is m here in place of, you have dou m by dou y. So in place of m you have t. So dou t. In place of y what you have, it is nothing but v. So dou t by dou v at constant x we said, that is yes. Dou n by dou x, that is in place of n what you have, p. So dou p, but there is a negative sign. So don't forget about the negative sign. You have to write that. Then dou x, that means yes in place of x. Dou yes, and what is constant? It is y. What is y? V. So how you got from this Gibbs equation? You got this Maxwell's relation. Like that, you have 4. These are the various 4 Gibbs equations, and you simply substitute what is m, n, x, y. So you get the respective Maxwell's relations. Very easy, right? This is a simpler way of getting the Maxwell's. Otherwise, what you have to do? You have to first find out this. You have to first differentiate, double differentiate, find this quantity and then this quantity and show that it is equal. Instead, this is simpler way of representing the Maxwell's relation. So you can ask to derive this Maxwell's relation. So it's there for both UG and PG actually. Then the next and the final law of thermodynamics is known as the third law of thermodynamics. So it is based on what is known as the Nernst heat theorem. Nernst he proposed that that in vicinity of absolute zero, all processes should take place without change in entropy and heat capacity. So what does he say? As the temperature approaches absolute zero, what is absolute zero? Minus 273 Kelvin. Okay, so a system when it is approaching that absolute zero, what happens? The entropy of the total change in entropy of the system approaches zero. It becomes zero when the heat capacity also approaching to zero. So based on this, that means what? What is it? What does this third law of thermodynamics it show? Based on the Planck, he extended this Nernst theorem, giving this statement that every substance has a finite positive entropy, but at 0K. That means it has got some entropy value at any other temperature, but at 0K. So at 0K, what happens? It becomes 0. The entropy may become 0 and does so become in case of perfectly crystalline substance. So there is no perfectly crystalline system. Always there is some amount of disorderness, defective structure that is present in any particular crystalline system. So this perfectness in the crystallinity is obtained only at that absolute 0. That's why it is defined that, because that is the driving force. Any perfect system will not have, energy, excess energy associated to undergo any change, any physical or chemical change. That's why a system need to have a defectiveness in the associated with it, so that that it has got some that excess energy, which is a driving force for it to undergo a physical change or a chemical change. Okay, so the statement implies that at absolute 0, the entropy of a perfect crystal is 0. So what is the molecular basis for this? That the entropy is the measure of randomness. This randomness becomes reduced when the temperature is decreased, goes to 0, goes on decreasing with the decrease in temperature, and it approaches 0 when temperature approaches 0. So in terms of this Boltzmann equation, that is the S is equal to K log W, we just talked about. W is the number of ways of molecular arrangements, that is the microstates. You can see here. What is happening here? At absolute 0, you have only one microstate possible. Perfectly aligned state, no? So there's only one microstate. The probability is the least. So there's only one state possible over there at 0K. No other randomness is associated. No other states are possible. So when you know that log 1 is nothing but 0, right? So W, when it becomes 1, perfect, only one microstate, log 1 becomes 0, and therefore what happens? At 0K, S is 0. When temperature is increasing, what happens? The disorderness starts here. Okay, the system goes into defective states. There's movement in the molecules, resulting into increase in the entropy or the disorderness of the system. So, but it's the other way. If it is going to low temperatures, it is 0. So this third law is very useful in evaluating the absolute entropies, because absolute entropies cannot be evaluated so easily, so calculated. So applying this third law, you can actually evaluate the heat entropies based on the heat capacities. It is given by this integral 0 to whatever is the temperature of the system you want to study, Tk, that is integral of Cp by T dt. Okay, this integral is not very easy to evaluate actually. So you actually plot the Cp by T versus T, and you extrapolate, because you cannot go to absolute 0, right, to evaluate any process. So you have to extrapolate that graph to 0 Kelvin, and I'll show you that. So therefore this absolute entropy is determined in terms of this integral value. Okay, this is nothing but the third law. This is also known as the third law entropy, this absolute entropy, because based on the third law. So it is used to determine for any particular process. Like for example, if you have to determine a system, a solid at any particular temperature, if you have to evaluate, you have to start the evaluating the entropy from the absolute 0, right? Suppose say a system is moving from state A, that is solid, to gaseous state. Okay, you want to determine what its entropy at this when it is in gaseous state at 290 K 1 atmospheric pressure. Then back onwards from absolute 0, you have to start that. For example, what are the steps that can be involved? There is some amount of heat required from moving it from 0K to a particular transition temperature, Tt. Okay, that T, it may have two different physical forms. That means alpha and beta forms, suppose say the solid state, physical transformation. So there is some amount of heat required from transforming it in from alpha form to beta form. And from beta form at temperature T, it should go to melting state. First, it should become liquid, no? Before it's going into gaseous state. What is the heat involved? Then from that melting state, what is the physical transformation occurring at that melting state? Heat required, that heat of fusion or heat of melting, whatever. Then from melting state to, it has to then go to boiling state. If it has got to go to boiling state. So what is the heat involved there? Then during the process of evaporation, that is latent heat of evaporation is involved. That plus now boiling point is, may not, the temperature 290 K may not be the boiling point. It may be higher than that. Then from the boiling point to 298 K, if you're going, what is it? So the heat involved. So many steps you have to evaluate the entropy to get the total entropy of the system at when it is in gaseous state at 290 K and 1 atmosphere. This is what I'll show. So these are all the delta S1, delta S2, delta S3, delta S. So all these 7 steps you have to evaluate the entropies. So at the fusion or melting or all, it is simply given by latent heat by T. Other processes, how do you know? It is Cp by T, integral Cp by T dt from the 0 to T or T1 to T2 or Tm to Tb, like that. Okay. So many steps you have to calculate to get the total entropy of the system, or you actually absolute entropies are obtained by plotting. I don't know, I've forgotten that graph actually. You plot this from this expression, you see this, you actually plot a graph. I'm not having annotations to draw anything here. Okay, anyway, so you have to plot this a graph between Cp by T on the y-axis to T on the x-axis. So it is not possible to go to 0. It is not easily achieved, no, 0 degree. But what is the entropy at 0 K? How do you know? You get the line graph like this between the two. You extrapolate it, extend it. So what is the value at absolute 0? That Cp by T value at absolute 0, if you know. From that, absolute entropies can be evaluated. Okay. So like this, some of the values are given for alkanes. You can see the absolute entropy values are given for chlorine, bromine, iodine, different entropy values. And for graphite and diamond, if you please compare that. Entropy of diamond is, graphite is 5.7 joules per kilo per mole, which is greater than that of diamond, 2.4 joules per kilo per mole. Okay. So you can see that there is less randomness in the diamond as compared to graphite, because graphite is a layered structure. There is more randomness associated. A diamond is a more ordered structure. Therefore, entropy of diamond is obviously much less. Alkanes, you can see that we are moving from methane to butane. The randomness is increasing, or the disorderness is increasing. From the absolute entropy values also you can see. So always entropy of a gas is greater than the liquid than the solid system. So finally we can summarize the whole thermodynamics. This is very nice and interesting diagram we can see here, the triangle. So it is moving around all the 3 laws. So and the principles are moving around these laws, and the properties between the mixtures, ideal systems, pure systems. So, and with the different processes. So thermodynamics is explained for reversible, irreversible processes and all. So this diagram explains what the gist of thermodynamics. So you can say that whole of it is moving around the main 3 laws. Yes, yeah, you have any queries you can ask. Before that, I just want you to repeat this. I always love the statement by Richard Feynman. He said, I can live with doubt and uncertainty. I think it's much more interesting to live not knowing than to have answers which might be wrong. So even after that, if you want to ask doubts, you can ask questions, no problem. Yes?
Girls, if you have any questions, you can unmute and ask madam.
If you are not asking, I'll be asking. So please make sure you ask questions.
I think no questions, madam.
Yeah, if you have no questions, I said I will ask. So may I?
Yes, ma'am.
Yeah. So yeah, before please don't give randomly answers. If somebody wants to answer, you can unmute yourself and answer, or you can type it in the chat. Okay. I'm not asking many questions, only 2 questions. And I'm giving some time to think. So those who give correct answers, you will get a gift. So you please, you can send your mobile number, which has got any GPay in the chat section. I can note down, or you can give your mail ID. So you'll get a small gift. So I'm just asking 2 questions. I'm giving you some time also. So please carefully read it and answer. Yes. These are all collected from, see all my data, everything. I'm very lazy. I collected it, everything from internet, just copy paste. Words are my words. I just didn't read out what are there in that. The words are my words, what I learned through years. But all the slides, most I've collected it from the internet to make it more interesting and to save my time. Okay. So the question, when a bottle of cold carbonated drink, so you people take aerated drinks, right? You drink. When a bottle of cold carbonated drink is opened, a slight fog forms around the opening. Why?
Due to condensation.
Who is that? Yeah, who is answering?
Rajshekhar, madam.
You mentioned the college.
Which college are you from?
Madam, Avanti College, PG.
Avanti
Organic.
College. Okay. So Kirtana madam teaches you?
Yes, ma'am.
Okay. So condensation of what? Be specific. Yeah, please. You're in right direction.
Madam?
Condensation of what?
Due to condensation, water droplets are occur on that body.
That's what condensation of what is taking place. See, when cold body, okay, you're saying cold carbonated drink is open. So what is happening? Please be specific. The bottle, I'm saying it is open, right?
Okay, madam.
So what is happening when you open the bottle?
I think diffusion is occurred.
Diffusion of what?
Diffusion of gas carbon dioxide.
So when diffusion is occurring, then why should fog form? Somebody, Deepthi, she's saying condensation of water. Karishma, she said pressure is decreased. Okay, pressure is decreased. Why should fog form? I think I'll give you the answer. Whoever is the closest. See, if you had remember the Jolt Thomson effect, so there is expansion. Pressure is decreasing, she said, but there is expansion. Adiabatically making the gas to expand here. So always adiabatic expansion, if you remember Joule-Thomson effect, I said, it is accompanied by Yeah, after I gave answer, you have typed. Karishma, adiabatic expansion of gas as temperature decreases when open, dissolved, escapes. Gas escapes into atmosphere, partial is decreased. No, not that. So it is adiabatic expansion of gas. It causes lowering of temperature, okay, and therefore condensation of the water vapor. So Rajshekhar, he said condensation of water vapor, and Karishma, she said expansion. I think half I can give you. So can you please, do you both have a GPay?
No, ma'am.
You don't have GPay. Mail ID unda? Do you have mail ID?
Yes, ma'am.
So please type that mail ID in the chat box. And Karishma, you have GPay? Or else you can give your mail ID. Jyoti, please do me the favor. No, you please note down both of their mail IDs. Karishma and Rajshekhar.
Okay, ma'am.
Thank you. Next. Yeah, this is the second question. Please read it. When a glass of hot milk is placed in a room and allowed to cool, its entropy decreases. Is it a violation of second law of thermodynamics? Because he said always, you know, a process, when hot thing, when it is placed, it will spontaneously lose heat, right? But as per the, you know, the second law of thermodynamics, what does it say? Entropy should increase, no? Always. But here entropy is decreasing. Is it violation of second law? No. Why? You know, simply yes or no, I don't want answers. I want the reasoning. I don't give any gift if you say yes or no. If yes, you have to explain. Even if it is no, you have to give the reasoning. I want the reason. I don't want yes or no answer.
Because, excuse me, ma'am.
Yes, Induja, please.
Ma'am, in the case of second law of thermodynamics, we had not learned about the how the like violation processes, like if a system is made to cool, we had not learned that there will be violation, all that sort. No, ma'am.
No, simple question. I said here there is an entropy decrease. But as per the second law, it says that entropy should increase, right?
Yes, ma'am.
So that way, is it violating the second law? You said no. Why is it? How is it not violation then?
Ma'am, the physical process can be reversed by heating the hot glass milk again when it's cooled down.
No, but we are not talking about any reverse. I'm simply asking. You have placed a glass containing hot milk. It will cool, right? So it is accompanied by decrease in entropy. Entropy decreases. But as per the second law of thermodynamics, entropy should, it's a spontaneous process, entropy should increase. Why it is decreasing? So are you saying it is a violation? If you remember what I told about entropy, and there is some other statement also I told you, I'm giving a clue. If you remember that, you can explain. dq is negative. No. Yes, dq is negative means delta S is negative. So you're saying not violation. Syed Sharif. Why not violation? Delta S should be positive, as per second law of thermodynamics. Okay, I think given enough time. If you had only remembered the Cauchy statement I have given, inequality statement. Okay, so body cools because entropy decreases because delta Q is negative. It's true. But if you individually see it as a system, delta S is negative. But I told you always you have to see it in holistic way. Both the system and the surroundings you have to see. Combination of this. The system is losing heat means the surroundings are gaining. So as in holistic view, if you see, delta S is not decreasing, delta S of universe is increasing. So nobody has given the proper answer for this, I'm sorry. So this is based on the Cauchy's statement, Cauchy's inequality. I already told you this, you have to examine. If you just think it in terms of the system, yes, it is violation. Delta S is negative. So the second law states that, delta S should be positive. The Cauchy's inequality, we said, what is it? Delta S by T, that is delta Q by T, that is delta S always should be greater than equal to 0, right? So that delta S is including that of the system and the surroundings. You have to take it in the holistic way. So it is not violation of second law of thermodynamics indeed. Okay, so for second, sorry, I cannot give, nobody has answered it properly. Delta Q, everybody is saying delta Q is negative, right? That is because delta S is negative is delta Q. Because delta Q is negative, only delta S is negative. But what I've asked, is it violation of second law of thermodynamics? It is not. That is should be, you just simply giving no as the answer and you do not know the reason, that is not correct. Isn't it? You agree?
Yes, ma'am.
So I'm so sorry, but better luck next time. Yeah, thank you all for attentive listening. Thank you so much, Jyoti and RBVER College. Give me this opportunity. Thank you one and all. And all of you stay healthy and stay safe. Thank you.
Thank you so much, ma'am. It was an interesting, excellent and informative session, ma'am. You covered almost all the concepts of thermodynamics, which is included in our syllabus, ma'am. And it is like a revision for our students who are going to write exam next week.
Hopefully it is of some help to them. Yeah, thank you.
Yes, ma'am. Ma'am, once please stop sharing, ma'am. I'll just share my screen.
I'll just stop it. Yeah. Yeah, I stopped sharing.
Okay. One second.
Oh.
Ma'am, from Department of Chemistry and Forensic Science, we would like to present a small certificate of appreciation to you, ma'am.
Thank you
Please
so
accept.
much. Thank you very much.
Thank you, ma'am.
Now thank you.
Yes, ma'am. Now I invite Dr. Umayma Ghazal, Assistant Professor in Department of Chemistry, to propose formal vote of thanks to Madam.
Good afternoon, everyone. I am Dr. Umayma Ghazal, gratifying to offer vote of thanks to our most valued resource person, Dr. A. Hari Padma Shri, Assistant Professor from Department of Chemistry, University College of Science, Osmania University, Hyderabad. Many thanks goes to Dr. Padma Shri for her treasured time with us and delivered lecture on the topic thermodynamics. Among the many capabilities of chemistry, thermodynamics has ability to predict if a process will occur under specified conditions. It is basically the study of relationships between the energy and work associated with chemical and physical processes, provides this predictive ability as well. So by today's lecture, we got the prospect to review the fundamentals of thermodynamics, which contains illustrations in terms of systems, surroundings, various processes, as well as state variables, state functions, etc., and the physical significance of thermodynamics, along with several visible examples yet again. She expanded the primary impact of thermodynamics on our daily lives in many ways, which shows us how to use energy efficiently and minimize the waste that inevitably accompany that use. She emphasized on thermodynamic equilibriums, which comprises of mechanical, thermal, and chemical equilibriums, along with examples. During her lecture, she defined enthusiastically all laws of thermodynamics and diverse important equations in an informal mode. Her talk gave an ideal knowledge to all the listeners, precisely the students who are fronting difficulty in studying thermodynamics. On behalf of complete Department of Chemistry, I want to recognize all the esteemed adherents of management of our college, our revered principal madam, Dr. Ashita Devi, who stimulated us to conduct with such informative assemblies. With profound sense, a great appreciation goes to our head of the department, Dr. V. Jeevna Jyoti, for her persistent determinations. I also express thanks to all the people who are present here. I'm closing with this expectation and remark that all participants absolutely got opposite information Dr. Padmashri, who stimulated us from her perfect acquaintance. Happy learning to all of you with great success in your future endeavors. And thank you everyone for your gracious presence. Thank you.
Thank you,
Thank you,
ma'am.
Dr. Mema.
Thank you, ma'am. It was really a wonderful elaborations which you have covered in all aspects of thermodynamics.
Thank you.
Thank you, ma'am.
Yeah, so can I leave now?
Yes, ma'am. Thank you so much,
Thank
ma'am.
you so much, Jyoti. Thank you very much. Once again.
Thank you. I request Prasanna to please post feedback form so that participants will fill.
Already posted, man.
Okay.